Okay, everyone. Last time we started talking about the physical properties of stereoisomers, and one of the things that we didn't quite get to was the discussion of optical activity. Uh, Optical activity is where you have a chiral molecule that is non-racemic and how it interacts with plane polarized light. So, just to give you an idea of how the experiment works, you basically have what's known as a polarizer, which takes light from a light source, which is typically sodium D-line light. And light, under normal conditions, has the electric vectors in all directions. And so the light source, with all of its directions of light, goes through the polarizer, and a single plane of polarized light comes through. And it turns out that these planes of polarized light, if you will, as they pass through a sample, they may or may not rotate their degrees. And so if you have um, a single plane of polarized light coming through a sample that contains an achiral compound, something like water or anything else that's not chiral, the plane goes through uh, the sample and comes out unchanged. So if you have this plane that's going up and down like this, so let's just call this 0 degrees, as it comes through, it's still at 0 degrees, and so no effect. However, the experiment is actually quite different when you have a non-racemic optically active material or chiral material. And so as this plane of polarized light comes through, it will actually rotate in one direction or the other. And so as you can see here, we have the plane of polarized light going up and down, but when it's coming out the end of the tube, it looks like it's rotated by a certain angle here, alpha. And so basically this analyzer is nothing more than another piece of polarizing material that allows us to determine how this plane of polarized light has actually exited the sample. And so it turns out that chiral molecules will rotate plane polarized light if and only if they are non-racemic. In other words, they have to be enriched in either the R or the S stereoisomer. So it turns out that there is a standard way to represent this. It's called specific rotation, and it's described as alpha, which means degrees, in a bracket. And that's equal to the observed rotation that we see coming out of the polarimeter, divided by the length of the sample tube times the concentration. And it's very important to remember, in this case, this is kind of an unusual concentration. It's actually in grams per milliliter, which really isn't a concentration, but this is going back to historical times when they did this. And the wavelength of light is typically 589. That's the sodium D line. But you can use other wavelengths. You just have to know what you're doing with that. And the length of the sample tube is in decimeters. So by definition, we almost always use a 1 decimeter tube, but you don't have to. But the L has to be listed in units of decimeters. And so you do the math and you can actually calculate the specific rotation. The cool thing about this is that you can actually use optical rotation to help you determine concentrations of molecules that are chiral if you know these other values. So for example, in the sugar industry, it's actually quite common to use optical rotation to determine the purity of sugar samples that come into a manufacturing plant. So when they refine sugar, they want to make sure that it is pure. And sugar is a chiral molecule, and they know the specific rotation of sugar. And so they know this value. They can determine this with the polarimeter. They know what their path length is. And so with a little algebra, they can actually solve for concentration. And so it's a quick and easy way to determine sugar concentrations in sugar syrups that come into these processing facilities. So I want you to work on this sample problem on your own before class tomorrow. So a solution of an optically active substance was made by dissolving 10.2 grams of the substance to make 1 liter of solution. The solution was then placed into a polarimeter tube that was 1 decimeter in length. The sample was then warmed to 26 degrees Celsius, and the polarimeter indicated that the sample rotated the plane of polarized light by negative 13.62 degrees. What is the specific rotation of this substance? So you need to solve this particular equation, and tomorrow when we go start class, I'll go through the sample problem on the board with you all. Some other things that we need to know about that you should have read. You need to know what an enantiomeric excess is. This is also known as optical purity, and it's a measure of how much one enantiomer is present in excess of the racemic mixture, and it's denoted by the symbol of EE. So the percent EE of a mixture is actually just the percent of one enantiomer minus the percent of the other enantiomer. So, for example, if we have a 3-to-1 mixture of enantiomers, so 75% of the compound is one enantiomer and 25% is the other, the enantiomeric excess is actually 50%. So you subtract the two numbers. And thus there is, 50% excess of one enantiomer over the other. That's basically what percent EE gives us. And we can actually determine EE a number of ways, but one way to do this is to actually measure the specific rotation of solutions. So if you have a specific rotation for the mixture of enantiomers, if you divided that by the specific rotation of the pure enantiomer and took that times 100, you'd get the percent EE. And it turns out that this is actually a very important concept. Like I mentioned the other day, with like the Aleve situation, you want to make sure you have one enantiomer of Aleve when you're taking it, because one enantiomer is what gives the therapeutic effect. The other enantiomer, like I mentioned, is actually very damaging to your liver to the point that it can actually kill you. So it's very important that you have molecules in medicine that are optically pure. That is, they don't contain the other enantiomer, and so they would have a percent EE of 100% essentially. And so you can determine that by optical rotation quite easily. I'll let you do this particular sample problem on your own. Again, I'll help you work out through it tomorrow. And so that finishes up what we needed to talk about yesterday. I'll get this up on YouTube for you as quickly as I can.